This is Timothy Wood with Citadel Civil Engineering. This is CIVL202 Statics, and in this lecture, we're going to talk about 2D equations of equilibrium. Up to this point, we've learned how to draw a free body diagram, and now we need to be able to write our equations of equilibrium in 2D. If we recall, our equation of equilibrium simply says that the sum of the forces, that's a vector summation, is equal to 0, yay, nothing moves. Now, when we think about this in 2D, we're going to have a couple of different ways that we can write this. One is using our Cartesian vector notation. So in this case, we would say the sum of the forces equal to 0, yay, nothing moves. That's so exciting. And we would come in here and we would say the sum of the forces in the x direction is equal to I, and the sum of the forces in the y direction is equal to j, or 0i plus 0j. And Cartesian vector notation is really nice because it tells us everything in kind of one line. So that's nice. We like that. Now, the thing that might be troublesome about this is we have to remember these I and j are perpendicular or orthogonal to one another. And so even though this looks like one line, it's not actually one equation. These two orthogonal components are actually independent of one another, meaning that this is really two equations. And so sometimes it's better for us, or we might prefer, to use scalar notation. So when we do this, we're going to have those two equations explicitly. So we're going to say the sum of the forces in the x direction with our scalar arrow is equal to 0. Yay, nothing moves. And the sum of the forces in the y direction equal to 0. Yay, nothing moves. So now, same information, but it really is explicit that we have two equations here. The reason this is important to us is because we're doing simultaneous equation solving, the number of equations we have must be greater than or equal to the number of unknowns we're attempting to solve for. Now, typically we'll know our loads and we're solving for our reactions, but this is the rule because we're using simultaneous equation solving. That's what we're going for, simultaneous equation solving. So we'll have two equations with up to two unknowns, and we'll need to solve for them simultaneously, either using substitution or elimination or a matrix method. I tend to prefer substitution, and we need to solve for that system. And then we'll be able to do a full particle equilibrium problem or a concurrent equations of equilibrium problem. I look forward to working an example with you in class, and I'll see you then.